It is my great pleasure to welcome our first speaker, Brian McDermott. Brian is a principal R&D engineer at NNL, the Naval Nuclear Laboratory, with a focus mostly on emerging technologies supporting the US Naval Nuclear Propulsion Program. Brian holds a PhD in nuclear engineering from Rensselaer Polytechnic Institute, and he's a former research reactor operator. He has a broad multidisciplinary experience in experimental physics, high-performance computing, now quantum computing, and scientific instrumentation development. Many of you have seen Brian on the Discord already, where he has been very active, sharing his own personal story as well, helping out with many questions. And this is not a coincidence. WOMANIUM is collaborating intensively with NNL on a variety of projects. So Brian, we are extremely happy to have you as a collaborator and very excited for your talk today. Please take it away with quantum for nuclear applications.
All right. Thanks, Marla, for the introduction. I'm going to start sharing my screen here. And give me 1 second. I run Linux, so it's the year of the Linux desktop. Can everybody see that?
Perfect.
All right. So yeah, I've been doing this program alongside a lot of you, and definitely, it's definitely very rigorous, and I'm definitely enjoying seeing all the energy and passion in the Discord, watching the chat go by. But I guess speaking of energy, my talk today is going to be on quantum technologies for nuclear engineering. So my story today is going to be mainly coming from the perspective as an end user of quantum technologies, not necessarily a developer like we've been hearing a lot of over the past couple of weeks. So I'll start out by giving an introduction of myself, kind of how I got where I got doing this, introduction of my lab and what we do, and then dive right into, what is nuclear engineering? What does that ecosystem look like? What are some of the basics that go into nuclear power production? And then go into what are the potential applications of quantum technology within this field, mainly focusing on the computing and sensing aspects of it. But as we'll see, it's a very underexplored field, and I think there's a lot of opportunities here for people to make contributions depending on what you're working on in quantum right now. And then finally, I'll give some words on workforce development, especially from the perspective of a non-quantum company and what it looks like to do workforce development in that type of environment, getting people ready for the future of quantum technology as it becomes adopted. All right, so about me. So I guess the first fun fact of personal trivia was that in the year 2000 was when I first discovered quantum computing. And so for those keeping score, I was in the 7th grade at the time. And I had picked up an issue of Scientific American, and it was about quantum teleportation, as you can see from the cover picture here. But what caught my eye was actually this kind of silly comic that was embedded in the article. It was called The Quantum Adventures of Alice and Bob. It was all about teleportation and then how you could actually teleport quantum information across the galaxy, and then, I guess come up with a better analysis than your competitor that only had classical communications. So kind of left that alone for a while. And then in 2003, I got into nuclear technology through nuclear fusion. And so it turns out there's this device that you can build in your garage called the Farnsworth Fuser. It was actually a fusion reactor that you can build as a hobbyist. So I started a side business selling old scientific equipment on eBay, and then used that to purchase other surplus parts to actually cobble this thing together, which you can see in the picture here. And that's what the pink star up there is actually what it looks like when it's running. So that was a fun, first foray into integrated product development, I guess you could say. And that's what got me into nuclear engineering. So I went to the Rensselaer Polytechnic Institute, which is up here in upstate New York, studied nuclear engineering for 10 years, both bachelor's and PhD. And basically what my PhD focused on was designing and building specialized instruments for doing neutron physics experiments. And along the way, I also became a licensed research reactor operator at the RPI reactor. So this picture here is of me standing inside the reactor tank, and you can see the fuel and the control rods and instrumentation there off to the left. And then the picture on the right there is actually the instrument I built for doing my PhD thesis, which was meant to measure how neutrons interact with various materials like iron and tantalum and lead, which is important for both nuclear energy applications, but also for more fundamental physics research involving astrophysics and how the elements are created inside stars, which I'll get to in a little bit later. And so now I'm a R&D engineer at the Naval Nuclear Laboratory up here in upstate New York. I got started in scientific computing and emerging technologies. I did a lot of work with HPC, multi-physics code development, and then picked up quantum technology in 2017, and I've been leading the technology development and integration part of that effort since about 2017. What really got me motivated for this, though, was there was actually a paper around the same time that came out of Oak Ridge National Lab that was about using a quantum computer and VQE to solve the ground state of the deuterium nucleus, which to that point I figured it's basically impossible to compute anything about the nucleus because they're so complicated, as we'll see in a few slides here. But that said, that indicated to me that, hey, there's a real opportunity for this technology to contribute significantly to the nuclear field. So mainly what I do now is this 0 to 1 integration type of activities, right? So this chart along the bottom, shows the technology readiness scale that we heard about a couple of weeks ago in Bonnie Marlowe's talk, where it's a scale of 1 to 9, where at 1 you're talking about like basic lab concepts, and at 9 you basically have a full scale production. I tend to operate in this 2 to 6 regime here, where basically you have a concept or an idea, but nobody's ever actually implemented it in an integrated fashion yet. So what I do is I take those ideas, work with all the stakeholders, assemble the thing, and actually develop a working product based off of that. So then a little bit about NNL then. The Naval Nuclear Laboratory and the U.S. Naval Nuclear Propulsion Program was actually founded right after World War II in 1946 by Admiral Rickover. And so it was he had the initial audacious idea of putting a nuclear reactor aboard a submarine in order to power it as the engine. And so today we're government owned. We sit under the Department of Energy, under the U.S. Naval Nuclear Propulsion Program, and we're contractor operated like many of the other Department of Energy laboratories that are out there. So right now our prime contractor is the Fleur Marine Propulsion Company. And so our lab is responsible for the full life cycle of all U.S. naval nuclear power plants. So this is the full stack of nuclear engineering, cradle to grave. We do everything. So that's the research, the design, the testing, the maintenance, and the ultimate disposal of the reactors. And so some unique parts about our history is that we've deployed and developed the first practical nuclear reactors for generating power. So the USS Nautilus was the first nuclear powered submarine. The USS Enterprise, which you can see in the picture here with all the crew standing on deck making the E equals MC squared, that was the first nuclear powered aircraft carrier. And then in an initial foray into tech transfer in the late 50s, the program was also responsible for developing the shipping port pressurized water reactor, which was the first commercial grid scale reactor in the United States. And then ultimately that reactor was reconfigured a few years later to actually run a thorium cycle. So it was also one of the first thorium powered reactors connected to the grid. So today we've got about 8,000 people spread across the country at 5 main locations. Our 2 primary research and development labs are the Bettis Laboratory in Pittsburgh, Pennsylvania, and the Knowles Atomic Power Laboratory in Schenectady, New York, which is where I work. We also have sites related to training the crews in Charleston, South Carolina, as well as our Kesselring site in West Milton, New York, and then the Naval Reactors Facility in Idaho, which handles a lot of the back end of the fuel cycle with the disposal. So right now, with all the ships that we've got out there, we've got about 80 reactors in service. So that's about 70 submarines, 10 aircraft carriers, which is comparable to the commercial nuclear reactor fleet in the United States as well in terms of electricity generation. And through all the years that we've been operating, over 75 years at this point, we have about over 7,500 reactor years of safe operation, perfect safety record. So we put out about 2 to 3 new reactors every year with every new ship that sets sail. And about 171 million ship miles have been traveled, or 275 ship kilometers traveled, which is almost 2 astronomical units of safe operation. So that we've gotten really good at this over the years. And so we're always looking to improve on what we do. So why do we care about quantum technology then? So in nuclear power, we often have to deal with these deep time scales. In our program, that approaches 100 years for some ship classes, and even in the commercial industry, it's also approaching those time scales because more and more people are realizing that it's probably not a good idea to shut down nuclear power if we're interested in carbon-free electricity. So the timescales that we have to operate on sometimes outlast and outlive the people who started those projects. So it's a very unique way of operating that's not very common in many industries. But on these timescales, emerging technologies matter. So when we talk about quantum technology being 10 years away, well, that's actually an important timescale for us. So we care about understanding what quantum technology can do for our industry, well in advance of actually deploying it, because we don't want to be playing catch up when this stuff becomes commercially available. We want to start getting our workforce prepared, getting our equipment prepared, getting our infrastructure prepared, so that way we can actually adopt these technologies as they become available. So at NNL, we started a quantum applications team back in 2015, which was even before I got there. It was initially to look at applications of quantum computing within the program. And it was kind of a casual, sort of like a lunchtime club at work type of thing. And then as the field really started to catch fire in the 2019, 2020 timeframe, we sort of expanded that to include some of these other nearer term technologies like sensing, materials, energy technologies, and things like that, and actually start getting more active in understanding what it can do for us. So to that end, we've got some current active projects going on in both algorithm development as well as some hardware with diamond nitrogen vacancy centers, which we'll talk about a little bit later. And ultimately, our quantum team's objective is to identify these impactful quantum technologies, develop our internal expertise and use cases, engage with external partners so that we can jointly develop and deploy these things, and educate both our current and future workforce to be quantum aware. So looking at what nuclear engineering is, nuclear technology you sometimes hear is considered being one of the first generations of quantum technology. And that's because nuclei have an inherently quantum mechanical description. When you think of the nucleus and, let's say uranium-235, right, with its 235 protons and neutrons, that whole thing is one really, really complicated wave function. And so interactions with nuclei and other particles are inherently probabilistic due to these quantum effects. And ultimately, the macroscopic behavior you see, both in power production, or talking about shielding, medical imaging, things like that. These are all determined and governed by quantum processes. And so nuclear engineering then is being able to harness these phenomena for useful applications. So energy production, which I'm mainly going to focus on today, so that's fission and fusion. Medicine, so that's your imaging and therapy, so your X-rays, your MRI, PET scans, cancer treatments, things like that. Safety and environmental protection. There's a whole industry surrounding radiation safety and keeping it out of the environment. Safeguards and nonproliferation. That's a very important topic these days, as well as instrumentation and measurement. So actually being able to build the instruments to detect and measure radiation and quantify it and figure out where it's coming from. And ultimately also there's fundamental science and astrophysics, because everything that happens inside stars is a nuclear effect. Nuclear engineers, we typically use many advanced tools and methods to do our work. So these are things like supercomputers, particle accelerators, research reactors, radiation particle detectors, fluid test loops, material synthesis characterization tools. The list goes on, you name it. It's a very rich and vibrant field where a lot of different disciplines need to come together in aggregate to build up, an integrated product that works safely and reliably for a very long period of time. So why pick nuclear energy then? What's really the motivation behind here? The primary one is that it's very energy dense. The nucleus has way more energy bound into it than chemical sources, just because that's the nature of how nuclei interact. The energies tend to be much higher. So you can think of uranium as basically fossilized supernova, where there's lots and lots of energy bound up into this nucleus that's sort of just waiting to be released. So gram for gram, it's about 100 million times more energy dense than fossil fuels. So looking at the pictures I've got here, this picture of the hand here holding a few pellets of uranium fuel, that's about equivalent to 500 kilograms of oil, which is about 3 barrels, 1,000 kilograms of coal, which is about the size of that pile in the picture there. Or if you're looking at more continuous energy sources like renewables, that's about 3 seconds of Niagara Falls, which is the largest waterfall by volume in North America, or about 1 minute of a mid-sized wind turbine farm, so about 50 megawatts there. So very compact facilities, very compact fuel source, very compact land usage with nuclear energy. It's also combustion free. So there's no CO2 emissions or pollution during operation. So, if you're concerned about climate change and decarbonizing the energy grid, nuclear power is certainly one of those power sources that's being considered for that. And the fact that there's no oxygen required also means that it works underwater and in space, which was originally Rickover's idea of why you'd want to put it on a ship in the first place. You don't need to refuel. And in space, the same thing. You don't need to carry along all that extra oxygen and hydrogen with you. you can have something that's very small and compact and have a lot of energy for a very small amount of weight that can get you very far in the solar system. And finally, it has very high availability. So in energy production, we talk about something called the capacity factor. So if something is always on, it would be about 100% capacity factor. With nuclear power, it's about 90%. So you have to shut down every couple of years to refuel, but more or less it's always on, always running at 100%, which is right now one of the leaders in all electricity generation methodologies. So diving a little bit more into how nuclear energy is produced, what it basically is a heat source. So you have some fuel, typically uranium-235, plutonium-239, uranium-233, that's packaged up and put into a pressurized vessel like this. It starts fissioning, it gets very hot, it makes heat, and then boils water, makes steam, spins a turbine, and that spinning turbine is used to generate electricity for land, sea, space applications, what have you. So as you can see, most of the work, so the heat generation part is really what the nuclear part is doing. Most of this other stuff is actually fairly common with all electricity production methods. And so really what we're doing is have a very complicated physics going into boiling a bunch of water. And so Albert Einstein even said it's a hell of a way to boil water. And ultimately that's what we're doing here, is just converting that bound up fossilized supernova energy into useful work for doing something. So how does quantum fit into all of this? Well, the intersection of nuclear and quantum technologies is relatively underexplored. So what I'll go into in a couple slides here is quantum computing has a lot of opportunities potentially in the engineering, design, and simulation aspects of this. There's a very, very heavy reliance on supercomputing in nuclear energy, and so quantum can probably contribute to that. There's also applications within the chemistry and material science side of things, as well as in the basic nuclear physics that go into informing a lot of how all these interactions occur. And then on the quantum sensing side of things, there are sensors everywhere in, whether it's nuclear power or medicine or what have you, there's sensors everywhere. And so there's lots of opportunities both in the laboratory, whether it's as well as in the manufacturing and plant process monitoring. And there's also some unique opportunities within the safeguards and non-proliferation space as well. But there's much more research is needed in this to really identify where all the opportunities lie. So first, quantum computing. As we all know, quantum computers can enable scaling improvements for problems that are typically encountered in nuclear engineering. So the types of engineering simulations you'll typically see are like finite element analysis, computational fluid dynamics, anything where you're solving a partial differential equation. That's the bread and butter of engineering calculations. And then there's also probabilistic algorithms. So these are things like your Monte Carlo, your Bayesian statistics, your machine learning calculations. And then finally, the first principle simulation. So these are the things related to material science, nuclear physics, chemical reactions. And so we at NNL, we're doing a lot of R&D efforts in this space. We right now have a active collaboration with the University of Pittsburgh, looking at different quantum algorithms for partial differential equation solving, numerical algorithms for that. And like Marlo alluded to earlier, we're looking at doing a quantum solutions launch project through WOMANIUM as well. So engineering simulation is really the central topic here when we talk about quantum computing. Computer simulations are essential for reactor design and maintenance. Pretty much, it's very hard to build things and do things experimentally because everything's so expensive and large. So we have to rely a lot on computational simulations. And these computational simulations can be expensive. So we're talking about detailed fluid dynamics. How does the water flow through this fuel assembly here in the picture here? There's lots of complex physics and interactions that go on in there, especially if you have phase changes. So you have water boiling to steam and things like that. When we talk about how is the power being generated, we have to do simulations where we go neutron by neutron and figure out where is everything happening. And then all that comes together in aggregate into a big multi-physics calculation. And so all this stuff gets coupled together, it feeds back on itself, and it gets very complicated. And then when it comes to the materials themselves are complex, and then the interactions between them are also complex. But it doesn't stop there, because you don't just do one calculation, right? You have to do many, many simulations to determine what does the design landscape look like? Where are the limits? How does everything fit together? So having to do this many, many times gets very expensive and requires a lot of supercomputing power. So quantum computing may be able to speed up some of these bottlenecks. But nuclear applications of quantum computing are not well studied. So we really need more research in this space to understand what benefits could it bring. The top one is something known as radiation transport. So this is a particular type of calculation that's very common in nuclear energy, as well as medicine, as well as astrophysics, and many other things where you basically have particles moving through a medium. We need to know how particles of radiation move and interact in various systems, because that tells us how power and heat is produced. It also tells us how the fuel is consumed, and it also tells us where the shielding is needed and how much of it is needed. And to do that, we use the Monte Carlo method, which we've probably heard about a little bit in the program. And so that's the gold standard for nuclear engineering calculations, because it's very accurate. The data we have is very accurate for that. And so it's limited by computational expense. And the way we do that is we first start up, we basically create a, almost like a CAD model of the system. And then we start a particle in some location, and then we let it fly and then track each collision and interaction that occurs and figure out where is the energy deposited. And so you have to tally all that up, and at the end you wind up with a picture looking like one of these ones along the side here, where it's almost like a heat map of where are the neutrons, where are the fissions, where's all the energy being released. And an interesting, historical fact here is that the early computers built during the Manhattan Project were actually built specifically for solving this problem, because it was very expensive at the time and nobody had any analytical math solutions for doing it. So really understanding that was important for that project. Now, as we've heard Monte Carlo from other fields, Monte Carlo should provide at least a quadratic scaling advantage for Monte Carlo problems. Is there an opportunity for better polynomial scaling or even exponential scaling in there? That's something that needs to be researched. And so the picture of this circuit here actually shows sort of a very simple quantum walk, right? Where you have like a 1D grid, say, of space points, and you're starting to say, okay, does a neutron go this way or this way, this way or this way? Then you track it until it finally gets absorbed in something. And so that's kind of like the first step into saying, okay, how would you actually implement this on future quantum hardware? The next big one is fluid dynamics. So, as I showed in the diagram a few slides ago, a working fluid is used to extract the heat produced by the nuclear fuel. Most common one in the world right now is water. There's other ones that involve using helium, carbon dioxide, molten sodium, molten salts like fluorides and chlorides. The list goes on. And so not only do we need to know how those fluids flow through all the structures within the reactor core and the piping and things like that, there's also you also need to keep track of phase changes. So things like boiling and condensation, as well as feedback effects with power production. So as power is produced, the heat is drawn away, the temperature goes down, that changes the properties of the nuclei, which then changes its properties of actually reacting in the first place. And so that whole thing is in a big tight loop that needs to be solved. And so accurate knowledge of fluid dynamics is needed because that directly determines the safety limits in a nuclear reactor. Knowing how you can get the heat out is important. It also impacts efficiency. So being able to get as much heat out as you can is important when you're looking at the economics of nuclear power attached to the grid. So quantum computing can improve the performance of these complex fluid dynamics calculations. And there's a lot of research going on, especially in the aerospace field, as well as now into more general sort of CFD solving, because this is a very economically important problem for a lot of industries. And so two of the most promising methods here are the tensor network methods, as well as the lattice-Boltzmann method, two of which that you'll see a lot in the quantum computing literature with regards to fluid dynamics. And so some of these pictures here are from our collaborators at the University of Pittsburgh that sort of used tensor networks to do these initial simulations of fluid dynamics, as well as this one up here on the top right was actually a quantum algorithm for simulating the mixing of two different species of fluid, and using a Monte Carlo method to do that. This one, material science and simulation of materials, comes up a lot in quantum computing, and it's nuclear power is no exception here. So understanding material properties is essential for the safety, reliability, and efficiency of a nuclear power plant. There's a lot of work going on these days in these inherently safe and high performance fuel systems. You'll sometimes hear about accident tolerant fuel. Corrosion resistant alloys. Corrosion is a hugely important thing for nuclear power, no matter where you are, as well as in other areas of the energy industry. And ultimately, when you talk about nuclear waste and spent nuclear fuel, coming up with materials that are robust and resilient over those tens of thousands of years timescales can give us more confidence in being able to store that stuff away for a very long period of time. But in the nuclear area, it's unique because accurate first principles simulations on these nuclear relevant materials are challenging. So we typically talk about things like the actinides. So this is your thorium, uranium, neptunium, plutonium. These have D and F orbitals that are strongly entangled and highly relativistic and very challenging to simulate using classical DFT methods. On the experimental side, those materials are expensive, radioactive, and require specialized facilities to even handle in the first place. So getting a real handle on how these things perform is challenging. And so typically these expensive computational methods that you have to use to, sort of understand the properties of things kind of limits the scalability of what you can do. So this is another area where quantum computing may be able to help. And so there's a lot of work going on right now in the quantum embedding methods, where basically you have some quantum algorithm that solves a subset of a classical density functional theory problem, density functional theory being, the computational method that's typically used to solve material science calculations at the atomistic scale. You have some embedding method where you have a quantum algorithm that solves some subset of that, and then that gets embedded in a more classical calculation. And similarly, tensor network methods also have opportunities in this space as well. So finally, in the quantum computing space is also the topic of fundamental nuclear physics. So when I mentioned earlier about those Monte Carlo simulations, all of that needs accurate nuclear data to even do the calculation in the first place. So we need to actually do experiments and take information on what do those interactions look like and what are the relative probabilities in order to even do the calculation in the first place. So getting that accurate data can tell us, what are the genesis of the heavy elements in stars, right? You start with something like iron, and then supernova happens, and all these neutrons collapse onto the nucleus all at once, and you get every element on the periodic table. Well, understanding that process there's still a lot of open questions about that. So being able to calculate properties of the nucleus can give us a better handle on that. And like we've been saying, the behavior of nuclear energy systems relies a lot on this nuclear data as well. And experiments aren't always practical. So we rely on experiments a lot for this, but sometimes we have either rare and expensive isotopes that we can only get micrograms of, or they're highly radioactive and they only last a few microseconds. So we can't really get a whole lot of experimental data on them. So that's why you might want to simulate this stuff from first principles. The problem is nuclei are too complicated to simulate from first principles. So electrons are hard because there's a lot of degrees of freedom. Nuclei are even worse. There's so many degrees of freedom per nucleon, so per proton and neutron, and all of them are strongly entangled. So once you get past oxygen, forget it. You cannot do, even on an exascale supercomputer, you cannot really do too much further than that in terms of simulating these things from first principles. And to add to that, the theories of how quarks and gluons behave in a bound system like a nucleus is actually incomplete. And so quantum computing is basically required for doing these first principle calculations on heavy elements, as well as for testing our theories of the strong nuclear force in the first place. And so there's a wealth of opportunity in this field as well for quantum computing to contribute to our basic understanding of the nucleus and how it assembles itself. So switching gears now to quantum sensing, like we've been hearing, over the past couple of weeks, qubits are very sensitive to environmental effects. So that makes fault-tolerant quantum computing challenging. But now you can turn that inside out and you can have very good sensors. And in a nuclear power plant, there are thousands of sensors. Literally everything you can think of has a sensor on it. And that's needed to ensure safe and reliable operation of the power plant. And all of these sensors need to last for many years under sometimes harsh conditions. So similarly, within the laboratory experiments and manufacturing processes, very precise sensors and detectors are required. So these are your things like your materials characterizations, your radiation detection. All those things need very accurate and precise sensing. So photonic quantum and photonic adjacent quantum sensors may offer some advantages here. So these are your things like your diamond nitrogen vacancy centers. So this picture here shows a diamond from the Element 6 company, actually, that's being hit by a green laser beam. And when that green laser beam hits it, it actually excites the nitrogen vacancy centers in the diamond, which act as qubits. And so the state of those at the time of the laser light readout will tell you things about your temperature, magnetic field, pressure, things like that. There's also plasmonic sensors. So plasmonic sensors are basically very thin films of a noble metal like gold or silver where you're effectively squishing light down into that metal. And then that can also give you information about the environment, like your temperature or chemical species presence. And this cool picture up here shows an ancient Roman cup that actually used a plasmonic technology many thousands of years ago, where when it's illuminated from the front, it looks green. And when it's illuminated from the back, it looks red. And that's because it has very fine particles of gold and silver in it. And that plasmonic effect is what causes that change in the color. And finally, there's also opportunities for photonic and fiber optic sensors as well, things that you like using entangled photons. So the first being process monitoring. So quantum sensors can improve monitoring of many different processes common, not just in nuclear energy, but also any real engineering application. So these are your lab studies, manufacturing, plant operations. Particularly when you have equipment that needs to run at a high reliability for a very high uptime, you sweat the small stuff. So little tiny problems can turn into very big problems quickly. And so you want to be able to pick up what are those little tiny problems before they turn into big problems. So quantum sensors with their high sensitivity have advantages there. And this can work for any real quantity of interest. So this is like your temperature, your pressure, mechanical stress and vibration. So this is if you're looking for stuff at like pump and motor fatigue. Fluid chemistry, like with plasmonics, if you're looking at the chemistry of the cooling water, you want to minimize corrosion. Monitoring that stuff is important as well. And so you can see in all these pictures here, there's lots of complicated stuff with lots of sensors on it. So there's lots of opportunities. And then a kind of a different application here, but an interesting one that's had some work done on it is on the issue of safeguards and nonproliferation. So tracking and securing nuclear materials like uranium and plutonium is critically important. This is for nonproliferation, both for treaty monitoring, as well as ensuring that illicit smuggling of materials is not occurring. But detection is very difficult because the quantities are small, the radiation is easily shielded. So you can think of something like a small piece of uranium or plutonium, very easy to shield. So some work that's been done at the other national labs of the United States actually showed that you can use cold atom interferometers, another type of quantum sensor, to do material verification and nuclear forensics. So these are things like tamper-proof scanning of spent nuclear fuel casks, like you see in the top picture here, which you can basically use the gravity difference of the fuel in the cask to determine whether or not it's been tampered with. And so this picture here kind of shows a raw calculation of what one fuel assembly in one of these casks would look like on a gravity gradiometer, like a cold atom interferometer here. You can also put them at a portal monitor at like a port of entry. So as like a vehicle driving through this would have radiation detectors around this portal, as well as gravity gradiometers that would detect the high density material of a nuclear material like uranium or plutonium. And then also employ data fusion with radiation measurements of gamma rays and neutrons to get a high level of confidence of what is inside a vehicle. Because there's lots of false positives that could occur from things like maybe the driver had a nuclear cancer treatment, or maybe there's a big crate of bananas in there that has potassium-40, which is radioactive, right? So being able to more confidently detect what is in something is important for the safeguards and nonproliferation application. And so finally, going on to the workforce development aspect of this, when you talk about a non-quantum organization that's interested in using quantum technology, what we need is a quantum literate workforce. So of course you need a core team of experts that can understand this technology deeply and match these technologies to business use cases. But in order for the technology to really get any adoption within your company, there needs to be a broader base of these user and support communities as well that can understand it, understand how to use it, and understand what are its unique traits that we need to support. And that enables informed decision-making on these new technologies as they come in, because a lot of something new will come out, will be heavily hyped, but you might not necessarily have the right information in order to make a good decision on that. And so that's why it's important to really train your existing workforce within a non-quantum company to really understand what can this technology do. And these early stage quantum efforts require multidisciplinary people and teams. It's an all hands on deck effort. So you need to have a strong understanding of your company's core business, but you also need to have a strong understanding of quantum technologies, as well as the enabling technologies. So not just the qubits themselves, but also the photonics, the electronics, the lasers, all this other stuff that goes into it in order to really integrate it into what you're trying to build. So my advice to that end is, if you're looking to go to a non-quantum company, would be to strive for excellence in quantum technology as well as another subject matter domain, because those two things are a force multiplier. And no matter what you do, whether it's technical or non-technical, there's room for everybody to contribute in this space. So to close here, I think there's numerous greenfield opportunities for quantum technology within nuclear engineering field, whether it be nuclear power or many of the other topics that I mentioned at the beginning, but didn't have time to cover today. And like I said, quantum computing may potentially enable some step changes in our abilities to simulate various phenomena that occur within, a nuclear system, both for design and maintenance. And quantum sensing will enable smaller, more durable and precise instrumentation across this industry, as well as the energy sector at large. So there's lots of opportunities there. And finally, all engineering organizations will require a quantum literate workforce if they want to adopt this technology in the coming years. So some final closing words from our founder, Admiral Rickover, who is, a unique kind of genius when it came to engineering management. The first thing he said here was that good ideas are not adopted automatically. They must be driven into practice with courageous impatience. So persist. And then the second thing he said was face facts brutally. So, sit down before the facts with an open mind and be prepared to give up every preconceived notion you have about something. So if the truth leads you into a place that, maybe you're wrong, be ready to admit that you're wrong. Face the facts brutally. He gave a good talk on something called paper reactors, real reactors, which I have the link to here. And he said the tools of the academic designer are a piece of paper and a pencil with an eraser. If a mistake is made, it can always be erased and changed. If a practical reactor designer errs, he wears their mistake around his neck. It cannot be erased and everyone sees it. So real things have real consequences, and it's always harder than you think. So be ready to look at the details. And to that end, the devil is in the details, but so is the salvation. So thanks for listening. Feel free to get a hold of me on Discord or any of these other options here if you want to, have questions or about, careers or anything like that. And we will be at the career fair on Friday. So, feel free to stop by as well.
Amazing. Thank you so much, Brian. The opportunities are so vast, and I actually encourage everyone to think about how can quantum contribute to all the topics and problems that Brian suggested. This is great, very inspiring talk. Thank you. And we will dive into questions right away because there are many. I know you are reading the Discord yourself as well.
Yeah,
Brian.
I'm kind of like scrolling through here.
We can do some good teamwork. Early in the talk, Diksha Singh asked, how are the radiation interactions measured in any medium?
Yeah, that's a good question. So that's like a whole other field of radiation detection. I didn't get a chance to cover today, but typically, when you talk about the different types of particles that are out there, you have, alpha particles, beta particles, gamma rays, and neutrons. And so, depending on which of those particles you're trying to measure, you typically build a different type of detector. So, alpha, beta, gamma, the most common one that you've probably heard of is a Geiger counter, right? So it's a very simple thing where a charged particle comes in, causes a cascade of electrons within the Geiger tube, and that creates an electrical signal that you can then read out on a meter and figure out, how much radiation do you have in that area. There's another type of detector called a scintillator. So the way a scintillator works is probably a little bit closer to the quantum technology, where you have a particle comes in, it interacts with some sort of crystal or organic material, and it creates a flash of light. And then that flash of light then travels into a photodetector, where it's then recorded as a signal and actually provides richer information about the particle that you detected, not just what kind of particle it was, but also its energy, and potentially, is it a neutron or is it a gamma ray? And so that gives you more richer information about what the radiation field you're looking at. And then finally, there's also semiconductor detectors. And so these are things that, think like a silicon, germanium, anything like that, where a particle comes in, usually gamma rays. These are usually good for gamma rays. Particle comes in, creates a particle or electron hole pair, and then those charge carriers, once again, traverse the semiconductor, and then you get a signal that you can then read out and analyze further. Semiconductor detectors are unique because they have a very high energy resolution, so they're good for discerning whether a gamma ray came from one material or if it came from another material.
Excellent.
And there's even, looking at the quantum side of this, superconducting semiconductor detectors are getting some, research traction now as well.
Great.
Which give improved energy resolution.
Excellent. Then a more general question. David from the US asks, is nuclear energy considered green energy? And Harsha adds, nuclear waste should be launched into black holes, the recycle bins of nature.
So I guess that's without getting into the messy politics of it, depending on, your definition of green energy, nuclear can be, right? Because it's during operation, it effectively emits zero carbon dioxide. There's also other challenges related to mainly the economics of it, right? Because right now with fossil fuels, especially natural gas in the United States, it's typically much cheaper to run those sources of electricity. So that makes for an interesting and economic situation when it comes to how do you prioritize what you connect to the grid. But when you care about carbon dioxide emissions, nuclear is it's right there with renewables in terms of its lifetime CO2 emissions.
Another general question from Miguel from Mexico. How does the public opinion in the US affect future investments in emerging technologies involved in nuclear energy? For example, Germany is shutting down their power plants a couple of years ago.
Yeah, so I don't have a whole lot of information on what the the current public opinion is generally on nuclear power, but I mean, like I was saying before, with the prioritization of decarbonizing the power grid, generally you're seeing more and more like state level governments now sort of trying to support keeping nuclear power plants open, even if the plan is to ramp up renewable power, right? You still want to keep as much carbon-free electricity as you can on the grid.
Many interesting questions are coming in. Artem asks, could you point out a quantum algorithm for simulating nuclear reactions?
Well, that's where the research is needed. So there are some. I can certainly post some papers in the Discord chat of past work that's been done, especially on the nuclear physics side of things. The folks at Lawrence Livermore have done a lot of first principles nuclear physics calculations that they're actively trying to map onto quantum computers right now.
Then Harsha asks, can you build a digital clone, a digital twin of a nuclear reactor using quantum computers like we do for spacecraft and classical computers?
Digital twinning is certainly a big topic right now in most engineering fields. So absolutely. Now on the quantum side of that, how does that all fit together, right? It comes down to which simulations make the most sense to run on quantum hardware versus sticking to classical hardware. But like pretty much any other engineered product out there, right? Digital twinning has a huge opportunity within the nuclear field as well as the energy sector more broadly.
There are a couple of questions about the materials. Do you expect that quantum computer can predict material properties better in the end than first principle methods here compared with density functional theory? So
forgive me because I'm not a super expert in the computational chemistry side of things, but the way I understand with density functional theory is that there's extensions to it based on Green's functions method, right? So the GW method is one that it typically gets thrown around a lot. And so quantum computing typically steps in for methods like that, where you have some sort of beyond DFT method that you want to implement. And then you're typically, taking the really expensive part, that many body correlation, and then that's the part that you're putting on the quantum computer. Then you're taking the solution from that and then somehow coupling it to the classical solution, and then probably running that iteratively. So one I'm aware of is the University of Chicago has a pretty deep program in this right now in these embedding methods, and there's certainly many others around the world as well that I'm probably not aware of right now.
It really incited a lot of thoughts and questions and ideas. Did you see one question, Brian, that you really want to answer?
Let me see.
Otherwise, I will ask one more. There were some questions about the Monte Carlo, if you use quantum Monte Carlo, or how you see that quantum computing will improve it.
So yeah, quantum Monte Carlo is a little different here because with that typically gets used in like the electronic structure and materials calculations. With the Monte Carlo I was talking about for radiation transport, what we're really simulating is actually a classical effect, right? So nuclear reactions are inherently quantum processes, but once that reaction happens, the quantum part's done. Really, we just want to figure out where are the particles going, where are they landing, how much energy are they depositing, and then tallying all that up and getting some aggregate answer.
Then last question from Ron, Chicago. Many countries use thorium-based nuclear reactors. Are there issues with thorium for naval vessels or land-based power plants?
So with land-based power plants, typically the thorium, like I talked about in one of the earlier slides, the thorium is typically put in a breeder reactor, right? So thorium itself is not a fissile fuel. What has to happen is it absorbs a neutron and then converts to uranium-233, which is that's the part that's actually fissioning and creating the power. So that's been demonstrated, like with PWR3, that's been demonstrated in a light water reactor. What's been much more popular lately has been these molten salt reactors. And so that's typically where you have some sort of thorium uranium mixture in like a fluoride or chloride salt. And that's actually liquid and it's circulating through the reactor and reacting that way. Those have been demonstrated on relatively like research scales, right? But there's a lot of challenges related to like the materials aspects of that, because molten salts being very hot are very nasty in terms of corrosion. And so eventually getting those things onto the grid and producing power is going to take a lot of development work and addressing those corrosion challenges, which certainly lots of people are looking at that.
Fantastic. The challenge is on. Think about what if you would do a project with NNL on quantum, what would it be? Share some ideas, share a scope, and there will be prizes for the best one. The challenge is on. Post them on Discord. Brian, thank you very much. We will keep being in touch on Discord, sharing ideas, answering more questions. This was amazing, very inspiring talk. And this is only the start of a new chapter, nuclear and quantum, with NNL, WOMANIUM, and everyone here. Thank you very much.
Thanks for having me.